Hi, Caroline Keats of ENRG Elements. ENRG Elements is an ASX-listed exploration company that's focused on the critical mineral space. We have uranium and lithium assets in Niger, and we recently submitted applications for permits in Manitoba, Canada, that are lithium prospective. Today, I have with me David Dabney, who is the MD of StarCore Nuclear, a Canadian company that is developing small modular reactors. In our sector, SMRs have been talked about for a long time, and to some extent, it's been rather elusive. Well, in terms of the discussion about development timetables and commercialisation. So I have so many questions. Thank you very much for being here, David.
Caroline, thank you for having me. It's a pleasure to be here, and I look forward to having the discussion with you.
Can you introduce us to StarCore and give us a bit of an overview of your business model in the small modular reactor industry?
Yes, StarCore is developing small modular reactors in Canada for remote locations, off-grid locations. We've been working on this for 10 years thereabouts, and we're in the process of developing a model that is a high temperature gas reactor. So in the nuclear reactor power world, there are pressurized water reactors, which are essentially most of the generation 1 and 2 designs. And then there's the Gen 4, which is not actually a new design, but it's basically it differentiates itself because it's in the high temperature end. So as opposed to 350 degrees centigrade operating temperatures, these are somewhere between 750 to, let's say, 1,000 degrees centigrade operating temperatures. And so we're in that space. We're slightly different because of the fact that we're focused on off-grid applications such as mine sites, remote communities, island nations, most of the locations where they're heavily dependent upon diesel, in some cases bunker C fuel oil, and where the cost of electricity is exceptionally high in terms of because of the transport, storage, cost of maintenance, and so forth. And so we can bring take the StarCore model in this off-grid application and deliver a series of benefits to the end users in these locations.
David, can you give us an overview of the design of StarCore's SMRs?
What we're looking at here is a artist rendition of basically the layout of the StarCore reactor. If we look at it from the side profile, which would be this one here, you're then looking at a structure that's probably 40 meters tall, 50 meters wide, and perhaps maybe 200 meters long in all. This end of the building, which you're looking at on the left-hand side, this is the basic balance of plant. This is where the majority of the operations take place. The other part of this is all the control systems as well as then the operations personnel. What you're seeing here, this white item here, or just sitting above the grade, that's actually a silo where the nuclear reactor sits. It sits in the silo approximately 15 to 20 meters below grade. And we do that for two reasons. One, for safety and security. And then the second reason is that generally in most locations around the world, once you get to 15 to 20 meters, then the Earth's temperature is a constant somewhere around 10 or 12 degrees C. And so that acts as a natural heat sink for the actual operations. So we get the benefit of that cooling effect for the silo where the reactor operates, where the reactor actually sits. And from a basically an aerial view, you're looking at, this would be the entrance to the facility. These are the two silos. You see, this is just a 2-reactor operation. The operations can take up to as many as 6 silos, where we'd have 6 different reactors, which would get you up over just over 100 degrees, 100 megawatts of output, 100 megawatts electric. And, but basically we try to remain and maintain a very low profile, because a lot of remote locations are pristine areas, and the last thing you need is a large structure that then disrupts the beautiful landscape. So we really try to keep it as low a profile as possible. And so this kind of then helps assure that. And as I said, then the actual silos are then part of the security measure in terms of keeping the reactors out of it. But the physical space that we require is minimal. It's you know, I mean, it's less than 10 acres all up in terms of the actual operations. We're working with the Canadian government to where we would have essentially a zero radius exclusion zone. And that would facilitate the fact that there are certain things that we can do because of the satellite technology involved, that in some of these remote communities, it would provide some things like telemedicine and education, as well as then, you know, the access to certain benefits through the internet connections that we could provide.
SMRs have been getting a lot of attention of late. So what sets SMRs apart from standard nuclear reactors? And what exciting applications and cost advantages do they bring to the table?
Yeah, you know, the most exciting thing about it is that it's kind of like the movement amongst the telephone, if you will. The telephone used to be a fixture on the wall, and you could call it up and talk to one other person. And today it just about delivers everything you could possibly want and fits in your pocket. And so SMRs are, in that sense, much more applicable in terms of delivering more than just electricity over the fence. So in particular, in the Gen 4 space, where you're talking about high temperature, there's a whole series of other assets that they can bring, benefits that they can bring to the community and the area that they're servicing. So in addition to electricity at a very affordable rate, because of the fact the modular design makes it much more efficient to design and implement, in addition to that, the heat values then create the chances for hydroponics in remote locations, or district heating in some cases, water purification, and then probably one of the biggest things which we've added to our mix is the development of hydrogen. So in a lot of these remote locations, particularly in the mining area, which you're familiar with, a lot of the heavy haul vehicles and equipment are dependent upon diesel. But the equipment manufacturers have already moved to developing hydrogen fuel cell vehicles and equipment. And so we'll be able to produce hydrogen on the spot, so you won't have to go through an extensive transport, storage, and you know, gasification requirements. We can actually then provide fuel to those facilities on the spot using the energy from our reactors. So it's a complex operation that basically then delivers a whole range of benefits. So it's not just power. It's actually a range of benefits that then reduce the cost to the end users substantially, starting somewhere at least 10 to 15%. And in some cases, like in the case of desalination, water purification, we can generate savings upwards of 50%.
We've been talking, when we talk about SMRs, there's all sorts of different levels of power generation. One, I'd like to understand where you are, because some of the SMRs are producing in the order of about 300 megawatts, and you know that will basically supply for a small town, or at least augment the other energy providers.
Size and so forth, and the range. Generally, SMRs are anything less than 300 megawatts. And then once you go, you're below 100 megawatts, they actually often refer to it as micro instead of just small. So we're in the range that our operations generate anywhere from 10 to basically 100 megawatts of power output, depending on the needs of the remote areas. Generally, what we've found is that most mining projects and most remote communities, generally the sweet spot is somewhere between actually about 30 to maybe 60 megawatts total power requirements. So in that area, we feel we can really address the remote communities in that area. So we're kind of on the smaller, we're definitely on the smaller scale in terms of the size overall.
When we talk about SMRs, one of the big things have been whether it's economic, whether the costs justify it, because whether the economies are there. So in terms of CapEx, are you allowed to discuss, and how does the OpEx side work?
Sure. So the one thing that will distinguish StarCore from most of the other developers out there is that the CapEx OpEx equation, although we share that information, basically where we're at is that in the case of mining companies or in the case of remote communities, the burden of actually going through the financials of setting up a nuclear operation is quite complex. So we go ahead and establish a long-term power purchase agreement, which in most cases is a significant savings over what they're currently paying for power. And we then provide the option of then providing them with water because of the savings we can generate there and some of the other benefits I spoke about. We then use that power purchase agreement as collateral on long-term financing for the operations. So basically the community or the mining company or whatever has no obligation in terms or no concerns in terms of all the complexities associated with the nuclear operation. We handle that because we know how to do it. That's what once we've done it, then we'll go back and work with the same regulators in terms of the Canadian Nuclear Safety Commission and the other government bodies that are then part of that process. So the CapEx, for instance, for us, in terms of cost per megawatt hour, in terms of the cost of construction, is somewhere around about $8,000 per megawatt. The OpEx on that is then somewhere around a quarter of that. So it's significantly less. So basically, we can deliver power to, when you go to off-grid sites, most off-grid sites, generally, they start somewhere, the full cost of electricity starts at somewhere around 25 cents per kilowatt hour, and I'm talking Canadian dollars in this case. And then it escalates from there depending on how remote they are and how difficult it is to transport the fuel. So I did an analysis with a diamond mine up in the Northern Territories, and basically they're paying somewhere on the order of about 85 cents per kilowatt hour for their power. It has to be shipped in the wintertime when the ice roads are in place. They have to store and carry at least 6 months worth of fuel at all times. And then, and just because of that, then it requires basically what they call an ARC grade of diesel in order to stand up to the weather that they have. So, we're looking at the fact that we can come in and actually probably cut their costs in about half of what they're currently paying. Most any ore body that you extract, one of the first stages of beneficiation at the mine site is typically to remove as many of the impurities that are basically easy to extract, right? Because the last thing you want to do is ship the waste material with the main ore to further processing in a less remote location. And so often that times, probably 80% of the times in terms of most of the resources then require both heat and water for that next stage of that first stage of beneficiation. We can provide that input to the facility as well at a much reduced cost.
Safety is a paramount concern in the nuclear industry. So how does StarCore approach and prioritise safety in the design and operation of its SMRs?
So first and foremost, the high temperature gas reactor has a special fuel that is designed where it is triple coated with basically a material that inhibits then its ability to go above a level of criticality. So it is what is known as self-limiting fuel. And so because it behaves in that manner from a physics standpoint, then the actual process is then designated as inherently safe, such that the most serious accident that you can have at any reactor is the loss of coolant. If the coolant here is lost for any reason, the reactor actually puts itself to sleep. So even though you would have backup equipment and that sort of thing in place as well, just by itself, the reactor will then go from full reactivity to zero reactivity in approximately 52 seconds. And when it does not then deteriorate. It actually is basically in a stasis mode. So the fuel doesn't deteriorate or burn up, and it doesn't then cause any other reactions or detrimental effects relative to the equipment or the surrounding facilities. The release of the coolant does not release radioactivity. We use helium gas, and helium gas cannot become radioactive because it is atomic as opposed to molecular. And so consequently, it just dissipates, basically, is what happens. And so you then fix where the leak came from, and then you pressurize the reactor, and it will resume operations. That's the first level. The second level of security that we have is, this shows basically a cutaway of the actual silo. So the silo itself is basically a double-walled silo. The core then sits inside of it. And on top of that reactor that then is here on the left, which fits in the center, there are then 4 lids, 1, 2, 3, and 4 lids. Each one of those lids weighs approximately, I think each one averages somewhere around 4,000 tons. Right. So you can't actually physically remove those lids. You have to have special equipment that then takes that out. You can't, it's not something that you could get a hold of because we only bring it out when we refuel the actual operations. And so we pull the core out very much like you would a battery, as it were, and then replace it with a new core. So it is totally, there's no back door or side ladder or access to the silo. And the silo, as I said, is a double-walled silo, so that it sits inside this, and then that wall then has basically a pressurized level all the way around the outside of the inner silo. On top of that, then we have basically an operation that then is controlled by satellites. And so what we do is, sorry, I meant to say it is monitored by satellites, not controlled. But we have a system that we developed where we have 3 satellites in space looking at each individual operations at all times. 2 of the satellites are basically geosynchronous, such that they are in space but sitting over the actual operations and collecting the data on the operations. And then 1 is a low Earth orbiting satellite, which then passes by and has adds a third eye to the operations on a periodic basis. The importance of the satellite is that satellite operations, depending on the end user, can then provide what's known as a keep alive signal. So at any time, if for any reason they need to shut the operations down, we can then just stop sending the keep alive signal. That basically is a coded message which goes through the satellite system. And if it isn't received by the operation within a timely manner, then it will just shut itself down completely. It'll go into that stasis mode. Since we operate on helium, we don't require water in our operations.
The complexities of the nuclear fuel cycle and the management requirements of this can be daunting. So how does StarCore plan to address these challenges to ensure that users of your SMRs have a seamless experience without having to deal with the nuclear fuel cycle themselves?
So because of the fact that we work off establishing basically a power purchase agreement and whatever benefits they might require, then they are not really exposed to that fuel cycle, because you're right, it is very complex. We are basically an operation where we license, construct, commission, operate, and decommission the operations for them, so that for the complete, cradle to grave, if you will, for the operations, we will then set it up so that all of those issues around that nuclear fuel cycle, which is so complex, are already wrapped up in the contract to supply the power. So it's something that we take care of way ahead of time. We basically set up the purchase of those fuels through a hedging process over a 40-year cycle. And then we, in addition to that, we take care of the fact that the waste is not left on site. And then the final thing, of course, is that we then set up essentially a sinking fund for the ultimate decommissioning of the facility, so that doesn't come as a burden to some future generation long after it was originally set up.
The energy landscape is constantly changing, and renewable energy sources have gained a lot of support as we move to decarbonised energy sources. How does StarCore envisage SMRs coexisting with renewable energy technologies? And what role do SMRs play in supporting a sustainable and diversified energy future?
It's actually an excellent fit. The reason why is that, as you correctly pointed out, the renewables have become established in many locations around the world, and in particular in remote locations. And so this would not supplant that, but it would support that. So one of the issues with renewables is that because it is intermittent power, then the efficiencies of it are often diminished because of the fact that they come or supplied at the wrong time. The sun doesn't shine at the right moments, so the wind blows at night when they actually don't need as much power. But with our operations, we actually can work alongside, because the dynamic output response time of our operations are such that if the renewables that are tied into the same grid start to supply more power, we can actually respond to that and generate less electricity and produce more heat. And since the heat is then going to other things like producing potable water or district heating or hydroponics and so forth, it's not being wasted. It's just being diverted to some of the other operations and benefits that come along with the facility. So we can use that to then make the actual renewables, particularly in the case of solar and wind, we can actually almost double their efficiency in terms of usable output.
Timeframes are always crucial in the world of nuclear energy. Can you share your development timeline and shed some light on what the future holds for StarCore and its SMR endeavours?
So we're starting the licensing process in Q2 of 2024. Over the next 6 months, we'll be working on the completion of the power purchase agreement with Manitoba Hydro. And that means that we'll be working through the details of the legal issues as well as completing the term sheet. We've also then set up our offices in Canada. And so we've then set up the various locations in Toronto, Winnipeg, Pinawa, and Ottawa. Ottawa being our licensing location with CNSC, Our headquarters is in Toronto, where our major contractors are located. Winnipeg, because we have to do quite a bit of correspondence and updates with the Manitoba government as things are progressing. And then Pinawa is actually the site where the White Shell labs are located. So we're at least 3 years away from commissioning the operations in White Shell. Once we start the licensing process, there's several stages to it. It starts with the vendor design review, the environmental assessment, the detailed engineering work, as well as then the construction and commissioning. One of the things that has come about, which has been a challenge for all of the SMR producers, was the availability of fuel. So traditional reactors on grid and so forth use fuel that has an enrichment level of somewhere between, say, 3 to 5%. Most of the SMRs are using what's known as a high assay fuel, which is basically somewhere between 15 and 19%. And fuel producers traditionally weren't able to actually produce that type of material. But a couple of companies here in the US and now in Europe are actually just starting to produce that. And so by the time that we get up and running, the type of fuel that we'll need will be available. And so the timing for us is actually quite fortuitous, because of the fact that that was like a major issue where some companies had gone through some of the licensing and testing and so forth, but they physically couldn't get fuel through the manufacturing process. So that's changed. And so for us, the startup on, as you said, in 2027 is approximately, that would be about the time frame commissioning of the operations. It'll probably take us somewhere on the order of about 3 months to commission the operations, but we are actually have an agreement with the licensing authority in Canada that we will then start licensing our second one probably a year from now. So we're actually working on the power purchase agreements with 2 other mining operations in Canada to then start the licensing on those probably a year after we start the licensing on this first one. Whoa. So the actual it's, you know, the future is bright. I mean, despite a lot of the turmoil that we see today, we believe that the development of SMRs will then actually create a tremendous ability for growth. We're working with the idea that ultimately we will be able to then export this to many other countries beyond Canada. We've had multiple discussions, as I said, with people in the Middle East about desalination. We've spent some time talking to people in Australia, mining companies in particular in Australia. We've gone out to some of the island nations and spent some time there. So the overall time frame in terms of what we see developing is that once we start and once we get the modular concept down, where essentially 85% of the plant is built off of a pallet, it'll be basically a plug and play type operation. We look at the fact that the market potential is significant, and the need is growing daily because of the environmental conditions that are occurring basically around us on an accelerated basis. So we feel really strongly that the business plan that we've been outlined, although it is attractive, is fairly conservative, because the actual need, when you start to dig below the surface and you see what's occurring basically on a global basis relative to the environment and its impact in a lot of these remote areas, we think that we have a huge challenge to get it going. But then once we get it going, we feel like there is just a tremendous opportunity.
Every time I talk to you, I learn a lot more about StarCore and the SMR space. I just want to thank you for being with us today and sharing your experience and more about StarCore with our viewers. This is really going to be a very exciting time as we're on the precipice of something great as we transition towards a clean energy future.
Absolutely. It's a pleasure. I really enjoy this, and really pleased that you invited me to speak.
Thank you.